Hello everyone, welcome back. So now we're going to try an example. It's a very simple one, just a boy kicking a ball, or a girl kicking a ball. And so we want to figure out is the horizontal distance it travels, as well as the velocity when it comes down at point C. And we know what velocity is at A, and we also know what the angle is at A. So let's see if we can figure out this problem. So how are we going to do it? Well, you're going to apply the kinematic relations in the x and y directions. So as always, I'm going to give you a few seconds to try this on your own. You can pause the video, go do it. If you can't figure it out, that's fine. The biggest thing here is you have 4 kinematic equations for projectile motion. Of those 4, you can use 3 of them, 2 in the y and 1 in the x. So look at those equations and see what can fall or what can come out of them. I think you'll quickly find you can figure out the answer. Okay, so with that in mind, 3, 2, 1, and you're off. You've done it. You come back and you rocked it, or maybe you didn't. Either way, we're here to do it together. So, first off, we know what the initial x velocity is and y velocity. We just have to break that velocity in the a direction up into components. You never get rid of that, okay? It's going to come all the time. Now, the velocity in the y direction after that initial moment is going to change. It's going to begin to decelerate and then eventually start accelerating towards the ground. We can also make an equation for the x position very simply because it's only velocity times time. And we can also find expression for the y position, which will be a function of time as well. Now here's our issue. We don't know how long it takes for it to go up and then back down again. So we're going to have to figure that out. And a lot of times that takes us doing a little bit of, just investigation here. So let's see what other information we can figure out. Well, one thing we can figure out is that y is equal to 0 at point C. So we change this to 0, and we look at this and we can solve. Now obviously if you look at this you're like, okay, well there's going to be 2 solutions, correct? Yes, one of those is trivial though. One of those is 0. At time equals 0, yes, it's going to be 0. So we can divide both sides by time, and we get this right here. We'll get 1/2 times 9.81 is equal to 10 sine of 30, which will just simply be 5. And then if we multiply this out, we get that the time, when it comes back down, the time it takes to get from here to here, or more properly since we're doing this in the y direction, the time to go up and then come back down, is 1.019 seconds. Now this helps us because I can now plug that into my equation for velocity in the y direction and plug it into my equation for velocity in the x direction. However, the answer at the end is fairly underwhelming. Because if you look at this right here, it's just 10 meters per second again. Wondering, well, why is that the case? Well, what goes up must come down. Since we have no friction, nothing to reduce the force to dissipate the energy, it has all the same amount of energy when it comes back down again. And so since all the velocities, velocity in the x direction is constant, the velocity in the y direction has to be the same, just in the opposite direction. There's 5 meters per second going up originally, and it's 5 meters per second going down afterwards. This is all because there's no air resistance. In real life, it would be slightly slower coming down. Now the horizontal distance the ball travels, we just put the velocity and we plug in our time, and it comes out to be 8.83 meters. Okay, so let's go back to our original equations again and look at them and see what we got. So we had those 4 kinematic equations. We didn't need them all, luckily. We only chose the ones that made sense. So we chose the one that gives us the x distance because we need that. We also had our equation for our velocity in the x direction, which is constant, and that's just taken from our component here. We have one for the y velocity as well. And we'll need that to be able to figure out what our velocity is at the end. So what we really had to do here, what we had to realize was that we know the y position at 2 points. We know it at the beginning and we know it at the end. And at the end, that's when we can solve for t. So it's not always 100% straightforward, but if you look around, you will find more information than you expect to be able to solve these problems. So I hope this helps you, and I'll see you all next time.